Part 1. Introduction. Today, we will construct a new mathematical universe. We will use a method called forcing to construct these universes. Forcing is a method invented by Cohen in 1963 to prove the independence of the continuum hypothesis. The continuum hypothesis asks, is there an intermediate infinity between the cardinalities of the natural numbers and the real numbers? The continuum hypothesis states that no, there isn't, but we will construct a model where there is one, so it's false. It was first asked in 1878 by Georg Cantor. In 1900, Hilbert presented a list of 23 unsolved problems, and the continuum hypothesis was number 1. Finally, in 1940 and 1963, it was proven to be independent of ZFC, meaning that we cannot prove it nor disprove it using the standard axioms of set theory. More specifically, he added aleph to many real numbers, called Cohen reals. In his new universe, there are at least aleph to many real numbers, so the continuum hypothesis is false. But we can't just randomly add a new real number and expect all the rules of math to work. And what exactly do we mean by mathematical universe exactly? And how can we add new real numbers to a mathematical universe in such a way that the rules of math still work? Part 2. Model theory. Before we begin, we need to define the concept of a mathematical universe. It's a universe where you can do math in. But this is a very vague definition. So let's try to build up some intuition by looking at something more familiar: fields. A field is basically a universe where you can do basic math operations on. That is, in a field you can add, subtract, multiply, and divide, just not by zero. Crucially, you never have to leave a field to do these operations. Let's look at the defining property of a field. It's a set and a collection of operations that satisfy certain axioms. These are the rules that something must follow to be a field. This pattern, a set, some operations or relations on a set, and a list of axioms show up again and again. For example, groups, posets, and equivalence relations. All of them consist of a set, some relations or operations on them, and they have to obey certain rules. A mathematical universe, or technically a model of ZFC, is basically the same thing. A model of ZFC is a set called M, a binary relation called in, that satisfies a certain set of axioms. The axioms that it must satisfy are the ZFC axioms. There are a lot more axioms, but fundamentally, a model of ZFC is no different from a group, poset, or equivalence relations, just with a different set of axioms. Part 3. A quick review of first-order logic. We said that a set with a binary operation is a group if it satisfies some axioms. But what do these formulas mean? What exactly is a logical formula? And what does it mean for them to be true? We can ask the same question for fields, posets, and models of ZFC. We need to define them precisely. First, we need to define the concept of a signature. Think of a signature as the words that have meaning in the mathematical language, and what kind of words they are: nouns, verbs, or adjectives. A signature consists of constants, relations, and function symbols. Each relation and function symbol has a number associated with it, called its arity, which is how many inputs it takes. More precisely, a signature consists of 3 disjoint sets called the constants, relations, and function symbols, along with a number associated with each relation and function symbol called its arity. For example, the signature of groups consists of 1 constant symbol for the identity, 2 function symbols with arities 2 and 1 respectively for the group operation and inversion. The signature of arithmetic consists of a constant symbol 0, a binary relation symbol for less than or equal to, a unary, which means arity 1 function symbol for successor, and 2 binary function symbols for addition and multiplication. And the signature of set theory consists of a single binary relation symbol for in. As an exercise, try writing down the signature for rings. A signature tells us what symbols there are. But the symbols don't have meaning unless we give them meaning. So let's do that now. An interpretation, also called a structure or model of a signature, consists of a set M called the domain of discourse, an element Cm in M for every constant symbol C, a function Fm from the n tuples of M to M for every function symbol F of arity n, and a subset Rm subset the set of n tuples of M for every relation symbol R of arity n. For example, a group consists of a set G, an element EG for the constant symbol E, a function G times G to G for the group operation, and a function inverse from G to G for inversion. And a poset consists of a set P, and the binary relation symbol less than or equal to corresponds to a subset of P times P. Every group is an interpretation of the signature of groups, and every poset is an interpretation of the signature of posets. Next, let's define terms and the value of a term. Terms refer to elements in the domain of discourse. For example, a term in the signature of groups just refers to an element of the group, and a term in the signature of arithmetic just refers to a natural number. For example, in groups, E, the identity, is a term, and for arithmetic, 3 plus 5 times 2 is a term. Terms are allowed to have variables, so in groups, x times y is a term, and in arithmetic, x times 3 plus 2 times y plus z is a term. A term consists of a constant symbol, a variable, or a function symbol applied to terms. More precisely, a term is a rooted tree where the leaf nodes are constant symbols or variables, and each non-leaf vertex is a function symbol whose number of children is the function's arity. For example, in the natural numbers with successor, addition, and multiplication, this is a term. As you can see, all leaf nodes are constants or variables, and all non-leaf nodes are functions. Remember when we said that terms refer to elements of the model? The value of the term is the element that it refers to. A variable assignment called sigma is a function from the variables of a term to the domain of discourse. Given a variable assignment and a term, we can define the value of the term, which is an element of a domain of discourse. It's defined by induction as follows. Every constant symbol C has the value Cm, and every variable x is given the value sigma x. If f is a function symbol, then its value is given by applying the function fm to the values of each of its inputs. Let's do some examples. Here's the definition again. In arithmetic, if the term is x plus 2 times y, and the variable assignment sends x to 3 and y to 5, then the value is 3 plus 2 times 5, which is 25. And in groups, in the group GL2 of R, if the term is x times y, and the variable assignment is this matrix, then the value is just a result of multiplying these matrices together. Here's another example. In arithmetic, what's the value of this term under this variable assignment? Next, we define formulas. Intuitively, a formula is a statement that can be true or false depending on the variable assignment. For example, in the signature of groups, here's one formula, and here is another. The first formula is always true. The second is true if A and B commute. But wait, we haven't even defined what a formula is, or what it means for a formula to be true. So let's do that now. A formula is also a tree. Each leaf node is an atomic formula, that is, the constants true, false, an equality of terms, or a relation of terms. And each non-leaf vertex is a logical operator, or the quantifier for all or exists, and a variable. For example, in arithmetic, these are formulas. In the natural numbers, the first formula is false, the second one is true, and the third one depends on the value of n. If phi is a formula and sigma is a variable assignment, we define the truth value by induction as follows. If phi is t equals u, where t and u are terms, then it's true if and only if t and u have the same value under sigma. If phi is a relation of terms, then it's true if and only if the values satisfy the relation. Remember that in an interpretation, Rm is a subset of the n tuples of M, where the M is the domain of discourse. If phi is a logical operator, then it's true if and only if the logical operator applied to the truth values of the subterms come out to true. That is, phi and psi is true if and only if both phi and psi are true, and similar for phi or psi or not phi. If phi is a quantifier for all x psi, then it's true if and only if for all m in the domain of discourse, psi is true under the variable assignment sigma m to x, where sigma m to x is the variable assignment that's the same as sigma for all variables other than x and sends x to m. Similarly, the exists x psi is true if and only if there exists some m in the domain of discourse, such as psi is true under the variable assignment sigma m to x. This should be very intuitive. A formula is true under some variable assignment if and only if it's true in the obvious way. Keep in mind, truth is a property of the formula, variable assignment, and interpretation taken together. That is, it does not make sense to ask, is this formula true? But only makes sense to ask, is this formula true under this variable assignment in this interpretation? The same formula can be true in one interpretation, but false in another. For example, in arithmetic, for all x exists y such that x plus y equals 0 is true in the integers, but false in the natural numbers. Let's do some examples. In the signature of posets, consider the formula for all x exists y, x less than or equal to y, and x is not equal to y, and the variable assignment can be anything. Is this true in the integers? Let's unwrap the definition. This is true if and only if, for all integers x, there exists another integer y, such that x is less than or equal to y, and x is not equal to y. But obviously, this is true, just like y equals x plus 1. However, if we consider any poset with a maximum element, such as the power set of the set x, then this is false. If x is the largest element, there is no possible choice for y. This shows that the truth of a formula depends not only on the formula itself, but also on the interpretation. Now, let's do another example. In arithmetic, consider natural numbers as the domain of discourse, and consider the formula for all x and y. If x times y is equal to n, then x is 1 or y is 1, and the variable assignment sends n to 17 and x and y to anything. This basically says that for all any natural numbers x and y, if x times y equals 17, then x equals 1 or y equals 1, which is true since 17 is a prime number. If we change the variable assignment so that n equals 15, then this will be false. And again, it's false in some other interpretations, such as the real numbers, even if n is prime. For example, 17 divided by 2 times 2 is equal to 17. You might have noticed something interesting here. It doesn't matter what some of the variables in the variables assignment were. Some of them were covered by the quantifiers for all and exists. An occurrence of a variable x in a leaf node of a term is bound if the term that the variable is in has a parent of the form for all x or exists x. An occurrence of a variable is called free if it is not bound. In this example, n is free while x and y are bound. The truth value of a formula does not depend on the values of variable assignment at variables that only occur bound. So, if phi has no free variables, called a sentence, then the variable assignment doesn't matter. Let's look at this example again. This occurrence of n is free since it has no parent of the form for all n or exists n. The occurrences of x and y are bound. So, let's do a recap of what we just covered. A signature is basically the vocabulary of our logical system. It tells us which constants, functions, and relations there are, as well as the number of inputs, called their arities. An interpretation, or structure, or model consists of a set called the domain of discourse, an element of M for every constant symbol, and a function for every function symbol, and a subset for every relation symbol. A term is an object that refers to something in the domain of discourse. Terms can have variables. A variable assignment tells us which values the variables take, allowing us to define the value of a term under a variable assignment. A formula is a statement that can be true or false depending on the interpretation and variable assignment. A variable occurrence x is called bound if it has a parent of the form for all x or exists x, otherwise it's called free. The truth value does not depend on the values of variables that only occur bound. A sentence is a formula that has no free variables. We can now define what a model of a theory is. Given a collection of sentences in a certain signature, a model is an interpretation where all of those sentences are true. So, a model of the group axioms is just a group. A model of a poset axioms is just a poset. And a model of ZFC is just a set M with a binary operation in M that satisfies all the axioms of ZFC. Note that there is also a notion of syntactic provability and a system called natural deductions that allow us to deduce new sentences from old ones using certain rules. This is a topic that is very interesting but not relevant to what we're trying to do. However, I'll give you a sneak peek. Natural deduction is a proof method that allows us to prove sentences from other sentences called axioms. We construct trees of sentences in a signature with added dummy constant symbols. Each tree's node has a label, which is a sentence, and it follows certain rules called rules of inference. The rules imply that each node's sentence follows logically from the previous ones. We can make assumptions, then discharge those assumptions when we no longer need them. For example, if we assume phi to prove psi, then we've proven phi implies psi from no assumptions. Disclaimer on set versus class-sized models. We will construct things that would be models, except the domain of discourse is not a set. Unlike sets, within ZFC we cannot define truth in a class model. This is due to Tarski's undefinability theorem. However, we can define a statement phi is true in C for an individual statement phi and class model C. We just need to use a different formula for each phi and C. We just can't define phi is true in C using a single formula with phi and C as variables. So if C is a class, then a sentence like C is a model of ZFC is not a single sentence, but an infinite collection of sentences. The collection consists of the sentence phi is true in C for every axiom phi of ZFC. Some fields have square roots of -1 and others don't. Anything we prove using the field axioms must be true in all fields. But there are some fields where it's true and some fields where it's false. So, using the field axioms, we cannot prove that square root of -1 exists, and we cannot prove that square root of -1 doesn't exist. A statement is called independent of a given set of axioms if it cannot be proven nor disproven from the set of axioms, assuming it's consistent. Thus, there exists x such as x squared plus 1 equals 0 is independent of field axioms, since we cannot prove it true nor false. This is a technique we will use to prove independence. To prove a statement is independent, we construct one model where it's true and one model where it's false. Any reasonable system of math has independent sentences, and the consistency of the system is one of those sentences. This is the famous Gödel's incompleteness theorems, which is a fascinating topic, but not the topic of this video. Part 4. Set theory. Let's do a brief review of the axioms of ZFC, ordinals, and cardinals. The signature of set theory consists of only one binary relation symbol, which is in. It satisfies the following axioms, called the Zermelo-Fraenkel axioms with the axiom of choice, or ZFC for short. The axiom of extensionality states that two sets are equal if they have the same elements. That is, all that matters is which elements a set contains. Two sets that are defined in completely different ways but have the same elements are the same set. The axiom of regularity states that every non-empty set has an element that is disjoint from it. The axiom of union states that we can take the union of all elements in a set, and that will also form a set. The axiom of pairing states that given any two elements, we can construct a set that contains just those two. We can also construct the singleton and the ordered pair. The axiom of power set states that we can construct a set of all subsets of a set. The axiom of infinity states that the set of natural numbers form a set. That is, there is a set that contains the empty set and that's closed under a certain kind of successor operation. The axiom schema of separation says that given any definable property, possibly with parameters, and any set, there is a subset of elements that satisfy the property. Note that we can only take subsets. The collection of all sets that satisfy the property might not exist. This restriction is to avoid things like Russell's paradox. The axiom schema of replacement states that given any formula phi that defines a class function, possibly with parameters, and any set S, the image of S under phi is a set. The axiom of choice says that given any collection of non-empty sets, it's possible to choose one element from each set. That is, there's a function from the set to the union of elements in a set such that f of s is in S. A well-ordered set is a totally ordered set where every non-empty subset has the smallest element. For example, the natural numbers is well-ordered, but the integers is not. The set of integers does not have a smallest element, so it's not well-ordered. Likewise, the closed interval from 0 to 1 is not well-ordered, since a half, a third, a fourth, and so on has no smallest element. The well-ordering theorem, which is equivalent to the axiom of choice, states that every set can be well-ordered. That is, there's some well-ordering on any set which might be different from the usual order if it has one, is a well-order. The well-founded recursion theorem basically tells us that it's possible to define a function recursively based on its values as the elements of a set. Here is the formal statement. We will use this when we construct the Boolean valued model of set theory and the names check x for sets S. The proof is basically by induction. For any set S, given the values of f of x for all x in S, the defining property tells you what f of s is. Now, let's define ordinals and cardinals. Since ordinals have already been extensively covered in other videos, and going in depth will take way too long, I'll only go over some basic properties. Ordinals are well-ordered sets. Each ordinal is a set of smaller ordinals. Each ordinal has a successor, which is the next ordinal. Every well-ordered set is order isomorphic to some ordinal, so that ordinal can be considered the representative, or technically order type, of the well-ordered set. By the axiom of choice, every set is well-orderable, so has a bijection to some ordinal. The smallest such ordinal is called its cardinality. Ordinals that are cardinalities have a special property. There is no smaller ordinal that has a bijection to it, so such an ordinal is called a cardinal. Aleph is the order isomorphism between the class of infinite cardinals and the class of all ordinals. So, Aleph knows the smallest infinite cardinal, Aleph finds the next one, and so on. The cardinality of a power set of a cardinal is known as 2 to the s. Cantor proved that 2 to the s is always greater than s. So, to recap, ZFC consists of 9 axioms. Every set can be well-ordered assuming the axiom of choice. We can define functions by well-founded recursion. Here is a statement. Ordinals are representatives of well-ordered sets. Cardinals are ordinals with no bijection to any smaller ordinal. Cardinals are representatives of equivalence classes of sets, where two sets are equivalent if there is a bijection between them. Aleph is the order isomorphism between a class of all ordinals and a class of all infinite cardinals. Part 5. The Continuum Hypothesis. The Continuum Hypothesis states that there is no intermediate size of infinity between the natural numbers and the real numbers, or equivalently, the power set of the natural numbers. We're going to prove that the continuum hypothesis is independent of z of c. We're going to use this the same way that I proved the independence of the existence of square root of minus 1. We just have to construct a model of z of c where it's true and another where it's false. Godel constructed a model of z of c where the continuum hypothesis is true, called the constructible universe. It's constructed by iterating the definable subset operation. A subset of a set is definable if there's a formula that defines it, possibly with parameters. More precisely, a subset T of a set S is definable if there's a formula with free variables x and y1 to yn and variable assignment sigma such that S is in T if and only if phi and sigma with x goes to S is true. There is also a level or a rank of each set called the ordinal rank, so that if x is in y, then rank of x is less than the rank of y. In this universe, Godel showed that every subset of the natural numbers that exists in his universe has a rank that is less than omega 1. There's just not enough room to fit another infinity. The topic of this video, however, is about the other model where the continuum hypothesis is false. Cohen then developed a way to add a lot more real numbers into a model of z of c called Cohen reals, at least I'll have 2 of them to be precise. This technique is called forcing. Note that our approach to forcing is Boolean valued models, which is different from the one Cohen introduced. It was developed shortly afterwards. Cohen originally used countable transitive models and generic filters, which cannot be proven to exist in z of c, even if we also assume z of c is consistent. Here's a brief proof sketch as to why a countable transitive model cannot be proven to exist in z of c, even if we assume z of c is consistent. Part 6. Outline of forcing. Let's give a brief outline of our plan. First, we generalize the concept of truth using a concept called a complete Boolean algebra. The truth values of statements can take on values other than true and false. We construct a Boolean valued model of z of c using the Boolean algebra B. We then use a tool called an ultrafilter to bring us back to a model of z of c where every statement is either true or false. By choosing a Boolean algebra correctly, the resulting model will contain an intermediate infinity between the natural numbers and the real numbers. We will then define two many functions from the natural numbers to 0, 1. The truth value of f of a of n is 0 or f of a of n is 1 will not be binary true or false, but a specific element of the poset that depends on a, n, and whether it's 0 or 1. Part 7. Boolean algebras. The first step in our outline is to generalize the concept of truth. Not every statement is binary true or false. Instead, we work with degrees of truth. The truth value of a statement is an element of a structure called a Boolean algebra, which is also defined as a set, constants, and operations on it, just like a group or field. The underlying set of a Boolean algebra is a set of possible truth values a formula can have. We can do Boolean operations on it such as and, or, and not. Let's give a formal definition. A Boolean algebra is a set B, two distinct elements 0 and 1 in B, and operations and, or, and not. It satisfies these axioms, which should be familiar from propositional logic. We can use these axioms to prove familiar theorems, such as De Morgan's laws. So basically, a Boolean algebra allows us to do logic, but with a bigger set than binary true or false. In fact, every formula that is a tautology in propositional logic has value 1 in any Boolean algebra. To prove this, we can put any formula phi into conjunctive normal form, and in a tautology, every clause has a or not a, which is 1. Conjunctive normal form means an and of ors. That is, a formula is in conjunctive normal form if it's a form a1 or a2 and so on, and b1 or b2 and so on, where each ai is a variable, the negation of a variable. To convert a formula into conjunctive normal form, do these steps. First, use De Morgan's laws until all negations are next to variables. Then, just use distributivity. Here is an example. We are now repeatedly using De Morgan's laws. We can now use distributivity. One example is the power set of a set, where AND is intersection, OR is union, and NOT is complement. These satisfy all the axioms that we've listed for Boolean algebra. Remember first-order logic? The power set of a set is a model of the axioms of a Boolean algebra. Power sets have a notion of when one set is contained in another. We can generalize this concept to any Boolean algebra. A is less than or equal to B if A implies B is 1, where A implies B is not A or B. Here are some statements that are equivalent to A is less than or equal to B. And this is indeed a partial order relation. The intuition is that A is less than or equal to B means that B is truer than A. Any situation where A is true, B is also true. Keep in mind that implies, not, and or are operators in the Boolean algebra. They take inputs and produce outputs. While less than or equal to is a relation that is either true or false for any pair of elements. Which means it does not make sense to say, is A and B true or false, because A and B is an element of the Boolean algebra. Since we have a partially ordered set, we can talk about upper and lower bounds. An upper bound of a set is an element that is greater than or equal to every element of that set. Similarly, a lower bound is an element that is less than or equal to every element of that set. A supremum is the least upper bound, and an infimum is the greatest lower bound. That is, a supremum is an upper bound that is less than or equal to all upper bounds including itself, and an infimum is a lower bound that is greater than or equal to all lower bounds including itself. For example, in a power set, the supremum is the union and the infimum is the intersection. Keep in mind, however, that since less than or equal to is only a partial order and not a total order, sups and infs can be weird. Being less than or equal to a supremum does not mean being less than or equal to some member of that set. Also, the sup of small sets can be large. For example, in a power set P of S, the supremum of all the singletons is the entire set S, but singletons are the smallest possible sets other than the empty set. So, unlike a totally ordered set such as the real numbers, the supremum of a bunch of small sets can be very big. And a set like 1, 2 is less than or equal to the supremum, but not less than or equal to any element of the set. So, supremum is large doesn't mean that the individual elements of the set are large, just that they're everywhere. Here are some properties of sup and inf. The supremum and infimum of two elements is just their or and and. Note that supremums and infimums of any subset, even infinite ones, are always unique, since an and of two upper bounds is also an upper bound. Sup and inf also satisfy the distributive property. And De Morgan's laws. Try proving them. However, the issue is that they might not always exist, which brings us to completeness. A complete Boolean algebra is one where sups and infs exist for any subset, even infinite ones. The completeness property is very important when you do Boolean valued models. So, let's do a recap of Boolean algebras. It consists of a set B, operations AND, OR, and NOT that satisfy familiar axioms of propositional logic. We can define a partial order on it, that A is less than or equal to B if A implies B is 1, where A implies B is not A or B, which intuitively states that any situation where A is true also makes B true. We can also consider the supremum and infimum of subsets of B, which are least upper bounds and greatest lower bounds, respectively. Although they don't behave the way we're used to, unlike a totally ordered set like the real numbers, the supremum of a bunch of small elements can be big. Part 8. Boolean valid models. We can generalize the concept of model to take values in a complete Boolean algebra instead of true or false. Recall that an interpretation in a set M called the domain of discourse, an element of that set for each constant symbol, a subset of the n tuples of M for each relation of arity n, and a function from the n tuples of M to M for each function symbol. We now allow formulas to have truth values in a Boolean algebra, not just true or false. The definition of a value of the term is the exact same, but the definition of a truth value of a formula is different. A Boolean value interpretation of a signature is defined similarly to a two-value interpretation, but takes values in a Boolean algebra. It consists of a set or class M called the domain of discourse, a function called equality from the pairs of M to B, a constant Cm in M for every constant symbol C, a function Rm from the n tuples of M to B for every relation symbol R of arity n, and a function Fm from the n tuples of M to M for every function symbol F of arity n. Note that equality and relations now have truth values in B instead of just true or false. We require that the following axioms hold. Everything is equal to itself with value 1. Equality is symmetric. Equality is transitive. Equal elements can be substituted into relations. Equal elements can be substituted into functions. There is an important consequence of the fourth axiom that allows us to determine when two elements of the Boolean algebra are equal. To denote the truth value of a formula, we use the double bar notation, and it's defined by induction as follows. If t and u are terms, t equals u has truth value given by the equality function on their values. For a relation, its truth value is just the interpretation of that relation evaluated at its values. For a logical operator, its operator applies the truth values of its inputs. The truth value of phi and psi is just the truth value of phi and the truth value of psi. Keep in mind that in the above statement, the two ands mean different things. The first one is the root node of a formula. Remember that formulas are trees. And the second is an operator in a Boolean algebra. For the universal quantifier, for all x psi is the infimum of the truth value of psi a for a and m. Note that here we need the Boolean algebra to be complete so that the sups and infs exist. And this is well defined even if the domain of discourse is a proper class. And for the existential quantifier that exists x psi, it's the sup of the truth values of psi a for a and m. For example, let's take the natural numbers as a model of arithmetic and add a new constant symbol c. And the Boolean algebra we'll use is a power set of the natural numbers. The domain of discourse is a set of all functions from natural numbers to natural numbers. 0 is interpreted as a constant zero function. The new constant symbol c is interpreted as the identity function. Successor, addition, and multiplication are all defined term-wise. And equality is just a set of numbers whose evaluations are equal. And the less than or equal to symbol is also interpreted like that too. Then, all of the axioms we've given for a Boolean value model are true. To prove it, we just unravel the definitions. Now's a good time to pause and try to prove it for yourself. And the truth value of a sentence phi containing c is just a set of natural numbers n, such that if we interpret c as n, makes phi true. So basically, we've just extended the natural numbers with a new element c, which is interpreted as the identity function, and not any constant function. If we take a free ultrafilter, we get a model of arithmetic with an infinitely large number. Now, a Boolean value model of a collection of sentences is a Boolean value interpretation such that all of those sentences have truth value 1. Remember, a sentence is a formula with no free variables. The soundness theorem for Boolean valued models states that if a set of sentences gamma proves a sentence phi, then the infimum of the truth values of the sentences in gamma is less than or equal to the truth value of phi. In other words, anything we can prove from a set of axioms is truer than the axioms. Again, if the domain of discourse is a proper class, we can make a similar definition of a truth value of a formula. But every formula becomes a class function from a class of variable assignments to the Boolean algebra B. And this class formula is defined by a different formula for each phi. By Tarski's undefinability theorem, there is no single formula SAT that takes phi and sigma and b and outputs whether phi with the variable assignment sigma has truth value b. And being a model is no longer a single sentence, rather is an infinite collection of sentences. So, to recap, a Boolean algebra is a structure that generalizes truth values. A Boolean value model consists of a set or class M and functions for each relation and function symbol, as well as equality. We've defined the truth value of a formula under variable assignment, which is an element of the Boolean algebra. This was our definition of truth. Part 9. The Boolean valued model of ZFC. We now construct a Boolean valued model of ZFC. It's going to be class-sized, since we cannot use ZFC to construct a set-sized model of ZFC. The intuition is as follows. Every set can be thought of as a function that says whether an element is in a set or not. In other words, a set is a function from the class of all sets to true and false. We will do a similar thing with Boolean value sets. Let B be any complete Boolean algebra. We want to say a Boolean value set is a function from the class of Boolean value sets to B. But we can't. That definition is circular. We used Boolean value sets to define Boolean value sets. So we instead define it using induction. The intuition is that an element of VB is a function S subset VB to B, such that elements of S have a smaller rank for some suitable rank function. Level 0 contains only the empty set. Level A for an ordinal A consists of functions whose domain is a subset of level little b over ordinals little b less than A, and outputs values in capital B, the Boolean algebra. Finally, the Boolean valued model is a union of the Boolean valued models of level A, where A ranges over the classes of all ordinals. Again, keep in mind that this is a proper class, not a set. Note that some textbooks use this different definition, which turns out to be equivalent to ours. Now, how to define equality and the truth value of x and y? Remember, we need to define it in a way that satisfies the conditions of being a Boolean valued model. And we want VB to be a model of ZFC, so we need the axiom of extensionality to be true. And we want basic facts about sets to be true, such that A is in B if and only if there exists x in B such that x equals A. Some trial and error gives us these definitions. Note that again this is an inductive definition, because in uses equals, which uses in, which uses equals, and so on. It satisfies an additional condition called fullness. Recall that we defined the truth value of exists x psi to be the supremum of psi of A for A in VB. Fullness means that this soup is reached by some element, that is, there is some A in VB such that the truth value of psi A is the truth value of the exists x psi. Likewise, we define the truth value of for all x psi as the infimum of psi A of A in VB. This infimum is also reached. This will be important when we use an ultrafilter to get a two-valued model. We also have these two properties for the truth values of exists x in S phi and for all x in S phi. I'll omit the proof here, but the proof can be found in any textbook that covers Boolean value models. The proof is basically to just apply the definitions and use fullness. Note that the element guaranteed by fullness might not be in the domain of S. This greatly simplifies the computation of truth values for delta zero formulas. A delta zero formula is a formula where all quantifiers have an in S attached to them. One more thing, we can embed V, the class of all sets, into VB as follows. The function check from V to VB is defined recursively by induction on the rank as follows. Check S has domain check X for X in S and sends every element to 1. Finally, I claim that VB satisfies every axiom of ZFC. That is, every axiom of ZFC has truth value 1. I won't give a full proof of every axiom, just sketch how to prove it. To see a full detailed proof, look at a textbook that covers Boolean value models. However, note that different textbooks might prove this theorem in different ways. For extensionality, use the definition of in to get this. Then take infs. Do the same thing again with x and y reversed. Take the AND of the two results to get extensionality. For separation, define y as follows. I claim that a is in y and a is in x and phi of a have the same truth value. First, we unravel the definitions a bit. Then we apply an axiom of equality. For pairing, if x and y are in VB, then the pair x, y is a constant function with value 1 on the domain consisting of x and y. Call that element C. By direct application of the definitions, the statement that for all z is in C if and only if z is x or z is y has truth value 1. For union, let S in VB be arbitrary. Let T in VB have the domain the union of the domains of elements of S and is a constant function 1. Then T is a subset of the union of S. We can take the true union by separation. For power set, let S in VB be arbitrary, and let T be this element shown here. Then the power set of S is a subset of T in the sense that every subset of S is in T has truth value 1. Again, we can use separation to get the true power set. For infinity, being the natural numbers is a delta zero property, so check of the natural numbers satisfies the axiom of infinity. To prove the replacement schema, we verify the collection principle instead, which is equivalent to replacement. Here is a statement. We use fullness on the existential part, and we take the set of all best values. For regularity, if the truth value is not 1, then consider the negation of the regularity axiom. Choose a counterexample S and consider the element y with least ordinal rank such that the truth value of y in S is not 0. Then, find one with smaller ordinal rank using the negation of regularity. Choice. Being well orderable is a sigma 1 property, so it's upwards absolute. So, for every set S, the truth value of the statement that check S can be well ordered is 1. If we can prove that every function has a surjective function from a well-ordered set, we'd be done, as a right inverse is an injective function to a well-ordered set. Let's talk about functions in VB. Note that from pairing, we have the unordered pair of two elements. It's an element of VB whose domain is x and y and is a constant function 1. If x equals y, then we get a singleton set x, whose domain is a singleton x and is the constant function 1. We also have this definition of an ordered pair. And this property of equality still holds. In set theory, just regular set theory, no Boolean value models, we have this formula for what it means to be a function, and these formulas for the domain and range. Note that we have two different concepts of domain here. The element of VB that serves the role of the domain of F, and the domain of an element of VB, since elements of VB are functions that have domains. Let dom superscript B of F refer to the element of VB, and dom F just refer to a domain of F as an element of VB. If F in VB has domain consisting of the ordered pairs xi, yi for some index set big I, and is a constant value 1, and this condition holds. Basically, if the inputs are equal, then so are the outputs. Then the truth value of f as a partial function is 1. The domain is the constant function 1 on the set of all xi's, and the range is the constant function 1 on the set of all yi's. Now we prove choice. Every element S of VB has a surjective function from check dom S to it. The domain of F is the set of ordered pairs check x for x in dom S, and F is a constant function 1. The internal dom B of F, is check dom S, which can be well ordered. And range B of F has the same domain as S, but is a constant function 1, so by direct application of the definition, it's bigger. Therefore, we have proven that VB satisfies all the axioms of Z of C with truth value 1. Part 10. The independence of the continuum hypothesis. So, for every complete Boolean algebra B, we can construct a class-sized Boolean-valued model of Z of C VB. If we choose a clever choice of B, the continuum hypothesis will be false in VB. Consider this. The real numbers are in bijection with the power set of the naturals, so a real number corresponds to a function from the natural numbers to 0, 1. We want to add at least aleph2 of these, so we want a function aleph2 times the natural numbers to 0, 1. F should be such that the functions little f of a are pairwise distinct. That is, for all a, b, and aleph2, there is some natural number n such that f of a n is not equal to f of b n. F is indecisive. It can't answer definitively yes or no to questions like, is f of a n equal to 1? We want a dedicated element of the Boolean algebra saying that f takes the value b at a n. And those dedicated values should also satisfy these requirements. We should be able to take the and of those dedicated elements to say that f takes value bn at an and n for various values of n. And f of an must be 0 or 1, and it cannot be both 0 and 1. We choose a partially ordered set P that are finite approximations to such a function. We start with the following poset. An element of P is a function whose domain is a finite subset of aleph2 times aleph null, and the codomain is 0, 1. Order these functions by reverse inclusion. That is, f is less than g if the domain of g is a subset of the domain of f, and the restriction of f to the domain of g is g. The intuition is that elements of P are constraints that capital F must follow. They are ordered by reverse inclusion, since a function extending another is a stronger constraint and thus less likely to be true. A dense subset of a Boolean algebra is one such that every non-zero element of B has a non-zero element of D less than or equal to it. We need P to satisfy a special condition called separative. P is separative if for all P not less than or equal to Q, there is some R less than or equal to P with no S that is less than or equal to both R and Q. If P is separative, we can embed P as a dense subset of a complete Boolean algebra using regular open sets. Here's the definition. Another way to construct the completion is using regular cuts, which are similar to Dedekind cuts. Either way, we get a complete Boolean algebra with our poset P as a dense subset. Again, requires P to be separative, and also crucially, 0 is not in P. We have a special notation a and b with these brackets for the function whose domain is a singleton set an and sends it to b. For any ordinal a less than omega 2 and natural number n, let Ra be the element of Vb whose domain is check and check b for natural numbers n and b in 0, 1, and sends check and check b to a and b. These Ra are called Cohen reals. Since each Ra consists of ordered pairs whose first element is a natural number, the statement Ra is a function from the natural numbers to 0, 1 has truth value 1 in VB. Now, we need to show that they are pairwise distinct. Ra is not equal to Rb if and only if they differ somewhere. So, the truth value of the same statement that Ra is not equal to Rb is greater than or equal to the conditions saying that they differ. The supremum of all conditions saying that they differ is 1 because they can appear everywhere. More precisely, if it's not 1, then some function p in capital P, our poset, is less than or equal to the negation of the supremum of the set of conditions where they differ. Call it S. But that P has finite domain, so there is some n such that neither an nor bn are in the domain. So we can extend P so it sends an to 0 and bn to 1, so it's less than something that says they're different. This is a contradiction. The last thing that we need to do is check that alpha2 doesn't change. This is because our poset satisfies something called the countable chain condition, which means that being a cardinal is absolute. The countable chain condition states that for any collection of elements of P whose pairwise AND is 0 in the Boolean algebra B, the collection is countable. We will prove it in 2 steps. That satisfying the countable chain condition implies that cardinals don't change, and that our poset satisfies the countable chain condition. We will use the soundness theorem. Here's a reminder of what it is. We will also use this formula for the truth value of bounded quantifiers. Here's a reminder. So, let's prove that being a cardinal is absolute if the poset P satisfies the countable chain condition. That is, if kappa is a cardinal, then the truth value of check kappa is a cardinal is 1. Being an ordinal is absolute since it's delta 0, and being omega is also absolute, so we assume kappa is uncountable. The goal is to prove that kappa is a cardinal. That is, for all x in kappa and f in VB, the truth value of the statement, if f is a function x to kappa, then f is not surjective, is 1. The first quantifier is bounded, so we look at only elements in the domain of kappa. Let w be the truth value of the statement that f is a function from check lambda to check kappa. We need to show that w is less or equal to the truth value of the statement that f is not surjective. If w is 0, we are done, so assume it's not. If f is a function, then for all elements of a domain, f of a equals b and f of a equals c implies b equals c. By the soundness theorem, this also holds in VB, which becomes this statement. Note that functions are defined in set theory as collections of ordered pairs. Recall that for 2 check sets, check s equals check t has truth value 1 if s equals 2 and 0 otherwise. Next, recall the definition of w, which we assumed is not 0. By density, there is some p in the poset P that is less than or equal to w. For a and lambda, let AA be the set of B and kappa that are possible output values of f of a. Here's a precise definition. Intuitively, AA is the set of possible values f of a can be. For every b in AA, choose a QB in P that is less than or equal to little p, and check A, check B is in F. If b and c are not equal and they're both in AA, then QB and QC is 0 by what we have above. So QB in P and our pairwise ANDs are 0. By the countable chain condition, the AAs are countable. So, to recap, kappa is an uncountable cardinal, lambda is an ordinal less than kappa, f in VB is arbitrary. Here's the definition of w. Little p and big P less than or equal to w is arbitrary. And the definition of AA for a and ordinal less than lambda is here. We have just shown that AA is countable. Our goal is to show that w is less than or equal to the truth value of the statement that f is not surjective. Since kappa is an uncountable cardinal, lambda less than kappa, and AA is countable. So the union of AA for all a in ordinals less than lambda is not all of kappa. Let M in kappa, but not in any of the AAs. For any ordinal a less than lambda, P and the truth value of the statement check A, check M is in F is 0. So P is less than or equal to the truth value of the statement F is not surjective, because again, the quantifier is bounded, so we just have to check elements in its domain. So, since P was arbitrarily less or equal to W, but the density of the capital P in the Boolean algebra, W is less or equal to the truth value of F is not surjective. So, we've achieved our goal that if P satisfies the countable chain condition, then the truth value of check kappa is cardinal is 1 whenever kappa is. Now, we just need to prove that our poset, the poset of functions from a finite subset of alpha 2 times alpha is null to 0, 1, satisfies the countable chain condition. As a reminder, here's what it states. What does it mean for f and g to be 0 when f and g are in the poset P? Remember, f and g are functions ordered by reverse inclusion. If f and g are elements of P and they're compatible, which means that they agree on all elements on the intersections of their domains, which is vectorsly true if the intersection of their domains is empty, then we can take their union. F union g is less than or equal to both f and g, so it's less than or equal to f and g. However, if they disagree somewhere, then there's no element of P that is less than or equal to both f and g, since such an element must extend both f and g, and that's not possible. So, by the density of P, we have that f and g is 0. So, f and g is 0 if and only if they disagree on some element of the intersections of their domains. So, we need to show that given any collection of elements S subset P, such that for any two elements f and g in S, f and g disagree on some element of the intersections of their domains, then the collection is countable. To prove this, we need to use the sunflower lemma. A collection of sets Si for some index set I is a sunflower if there is a set K called the kernel, such that for all I not equal to j in capital I, Si intersect Sj is equal to K. The sunflower lemma says that for any Si with the index set I uncountable and each Si is finite, there's some j subset the index set I which is also uncountable, such that the set of Sj's is a sunflower. First, consider the set of elements In such that Si has cardinality n. At least one In is uncountable. Thus, replace I with In, and we assume that each Si has cardinality n. We go by induction. For the base case n equals 1, each Si is a singleton set Ai. Define an equivalence relation on I such that little I is equivalent to little j if Ai is equal to Aj. Then, if one equivalence class is uncountable, that's a sunflower. If not, then the number of equivalence classes is uncountable. Choose one from each class, and those sets are pairwise disjoint. Now, we do the induction case. If there is some element little s that is in the set Si for uncountably many I in the index set big I, replace the index set with the set of elements such that little s is in the set Si, and apply the induction hypothesis to the sets Sj minus little s for j in the restrictions index set. Otherwise, every little s is contained in only countably many sets Si. We find an uncountable collection of pairwise disjoint sets using transfinite induction. That is, we will define a function f from omega 1, the first uncountable ordinal, to the index set I, such that S of f of a intersect S of f of b is empty for all a not equal to b. F of 0 is arbitrary. For any countable ordinal a, consider the set of all invalid choices. The union of previously chosen sets is a countable union of finite sets, so it's countable. Each an is in Si for only countably many I, so the set of invalid choices is a countable union of countable sets, which is countable. So the union is not all of the index set I. Let f of a be any element of the index set I that is outside that union. So, to recap, we want to show that being a cardinal is absolute. That is, if kappa is a cardinal, then the truth value of check kappa is a cardinal is 1. We have reduced this to showing that if S is a subset of P, and for all f and g in S, there is some element in their intersection of the domains that they disagree on, then S is countable. Suppose S is uncountable, then, by the sunflower lemma applied to their domains, there is a subset T of S, also uncountable, and a finite K subset of 2 times L of null called the kernel, such that if f and g are in T, then the intersection of the domains is K. We assume that f and g disagree on some point in the intersection of the domains whenever f and g are in T. So the restriction map T to the functions k to 0, 1 is injective, which can't possibly be true since the left side is T, which is uncountable, and the right side is finite. Thus, we're done. check kappa is a cardinal whenever kappa is. So we have check aleph null, check aleph 1, and check aleph 2 are all cardinals with truth value 1. And check aleph null and check aleph 1 are both in check aleph 2 with truth value 1. So the statement that check aleph 2 is a cardinal with at least 2 smaller infinite cardinals has truth value 1. Consider the element of VB whose domain is check A RA for ordinals A in aleph 2 and is the constant function 1. Let's call it f. Then in VB, the statement f is a function whose domain is aleph 2 and codomain is a set of functions aleph 0 to aleph 1 and is injective has truth value 1. Since VB assigns the truth value 1 to statement RA is a function aleph 0 to 0, 1 and the truth value 0 to RA equals RB whenever A is not equal to B. Thus, VB satisfies the negation of the continuum hypothesis, since there is a function aleph 2 to the power set of aleph null that is injective. Part 11. From Boolean value class models to two-value set models. We are almost done, except we have a few last issues to address. The class VB is not a set, and it's a Boolean value model, not a two-value model. How do we fix this? We address the second issue first. Choose an ultrafilter on B to collapse it to a two-value model. An ultrafilter on a Boolean algebra is a subset that satisfies these axioms. Ultrafilters on a Boolean algebra exist by Zorn's lemma. The idea is to take off filters which are subsets satisfying all axioms except for the last one and take the maximal filter. Now, define an equivalence relation on VB such that x is equivalent to y if and only if the truth value of x equals y is in the ultrafilter. On the collection of equivalence classes, define that A is in B if and only if the truth value of A in B is in the ultrafilter. A power theorem called Walsh's theorem says that if M is a full Boolean value model and the statement's truth value is in U, then it's true in the quotient M quotient U. To prove it, we use induction on the formula. We need fullness to prove the part with quantifiers. Putting it all together, we have a formula phi with three variables x, b, and u that states B is a completion of the poset P, U is an ultrafilter on B, and X is an equivalence class of VB. And a formula in with four free variables x, y, b, u that states phi of x, b, u and phi of y, b, u, and the truth value of x in y is in u. We can transform any sentence in the language of set theory as follows. Replace x in y with in x, y, b, u, and restrict all quantifiers to phi of x, b, u. That is, replace all instances of for x psi with for x phi of x, b, u implies psi, and exists x psi with exists x phi of x, b, u, and psi. Here is an example of a formula being transformed. The work we did before implies that ZFC proves the transformed version of every axiom of ZFC, and ZFC proves the transformed version of the negation of the continuum hypothesis. Our goal was to construct a model of ZFC where the continuum hypothesis is false. So let M be any set model of ZFC, where in M does not have to be the same as the actual in. Since ZFC proves the existence of Boolean algebra and ultrafilter U that satisfies the criteria we put out, there are some B and U in M that satisfy the property of being such a Boolean algebra and ultrafilter. Since ZFC proves the transformed version of every axiom of ZFC and the negation of the continuum hypothesis, the transformed version of every axiom is true when we take B and U as those elements. Thus, if we define the subset N as the set of X in M such that phi of X, B, and U are true, and the relation in N, which is a subset of N times N, that's such that in of X, Y, B, and U are true, then N and in N form a model of ZFC where the continuum hypothesis is false. Note that this is well defined even if B and U are not in N, since in N is just a subset of N times N. Another way to derive this result is to transform the proofs instead of taking a model. Suppose that ZFC proves the continuum hypothesis. Then ZFC plus the negation of the continuum hypothesis is inconsistent. So there's a proof of false starting from the axioms of ZFC plus not CH. Transform every formula in the proof using the above method. You get a proof of false whose axioms are the transformed versions of the axioms of ZFC plus not CH. And since ZFC proves the transformed version of every axiom of ZFC plus not CH, transforming each line of the proof results in a proof of a contradiction in ZFC. So if ZFC proves CH, then ZFC is inconsistent, and it gives an algorithm as well to convert a proof of a contradiction in ZFC plus not CH to a proof of a contradiction in ZFC. Part 12. Further topics and conclusion. In the constructible universe, CH holds. In our new universe, the negation of CH holds. So if ZFC is consistent, it neither proves nor disproves the continuum hypothesis. Thus, we have achieved our goal. Now, I want to talk about some other more advanced topics. We can also use forcing to prove Easton's theorem, which is a generalization of the independence result we've proven here. It basically shows that in ZFC we have very little control over what the power set of a set can be. 2 to the alpha null can be almost anything, but not cardinals with countable cofinality such as aleph omega. We can also use forcing to collapse cardinals, meaning that 2 different cardinals become the same one. If lambda is greater than kappa and are cardinals, the poset we use is a set of functions from a subset of kappa whose cardinality is strictly less than kappa to lambda. In the universe VB quotient U, there is a surjective function check kappa to check lambda. We can also use it to prove the independence of the existence of Suslin lines. A Suslin line is a totally ordered set that behaves similar to the real numbers. Here is the precise definition. If the axiom of constructibility holds, that is, every set is in L the constructible universe, then there are Suslin lines. And if Martin's axiom plus the negation of the continuum hypothesis holds, there are no Suslin lines. To prove that Martin's axiom plus not CH is consistent, we use, you guess it, forcing. More precisely, Robert Solvay and Stanley Tannenbaum use a technique called iterative forcing with finite support. There's a lot more to cover. Look at any textbook on advanced set theory. The end. Thank you for watching.